Come on, come on. Okay. So, what's the takeaway of that buys us the vortex formula? So, this is hard to graph just as is, but that's suddenly easy to graph by transformations. You'd start with just y equals x squared. If a is negative, you flip it and stretch it, otherwise you just stretch it some. You move left by b over 2a, then you move up by that much. As a consequence, you know automatically that any graph, any quadratic function's graph, will look like this. You'll have this vortex point at x value negative b over 2a, y value c minus b squared over 4a. And from that, you can read off exactly where the maximum or minimum occurs. And then we just encoded that in this theorem called the vortex formula. Quadratic function f of x equal to ax squared plus bx plus c has vortex at x equal to negative b over 2a, because that's what the graph above says. Could we also have recorded the y value of that? Yeah, what is the y value? Yeah, exactly that. If a happens to be bigger than 0, the vortex minimizes, because it's an upward opening parabola. If a is less than 0, the vortex maximizes, because it's a downward opening parabola. Well, there's some ellipses there at what happens when a is equal to 0. If a is equal to 0, what can you say about the graph of this function? Say that over. It's not just 0, only the a term is 0. So you still have bx plus c. Yeah, it's a line. You already know how to deal with linear functions, so you don't need a vortex formula for linear functions. They don't have a vortex. Let's talk about why I don't really regard this y value as part of the theorem. We could write it down and record it just as easily. But if you already know the input you should plug in to maximize a function, how do you figure out the output that maximizes the function? Well, let's see this in practice on the next page. Let's do an application, then I'll flip back here and say why this pulpal bit I don't regard as an important part of that result. So, here is an example of using this formula to optimize. So, here's a long-winded setup. In order to keep away prying eyes, you have some secret. You're constructing a fenced-off area, one side of which is adjacent to a cliff face. You don't need to fence off the cliff face, because if someone's going to climb something, they'll climb your fence anyway, not the cliff. So you don't need to fence off the cliff face. You've got 1,000 feet of fencing, and you're going to enclose a rectangular region with this amount of fencing. The more area you can capture, the safer your secret will be. There's more places to dig. What arrangement of fencing will let you maximize the area that you can enclose in your fence? That seemed like a reasonable thing to try to do. Right, you've got some amount of fence, you want to enclose as much area as possible. So let's just try to set up the problem. It's a rectangle that we're trying to capture. So what parameters does a rectangle have? If you wanted to describe a rectangle exactly, what information do you need to give? Yeah, it's got 2 dimensions. So let's just parameterize this problem. It's got some length of fencing and some width of fencing. So let's play this game. Let's try to get a relationship that L and W have to satisfy. We'll try to get a formula for the area. We'll hope that it's a quadratic. If it is, then we can not complete the square, but instead just use this vortex formula to say what should maximize. So let's start with this. You've only got 1,000 feet of fencing. So what does that that give you a relationship between L and W? I think it gives you something, though. You've got 1,000 feet. So that's like the total length of fence. If you want to build your fence according to this diagram, how much fence would you use in terms of L and W? Yeah, say louder. Not 2W. One of the instructions, well, you don't actually build fence along the cliff wall because you don't need to. So 2L plus W is the amount of fence you used. Oh, neat. So 1,000 feet is equal to 2L plus W. Maybe I'll suppress the units and we'll just remember that distance is being measured in feet. That looks like something you could solve for either L or W. Which would you rather solve for? Which does it seem easier to solve for? Yeah, but just say it louder. Yeah, right, there's no 2 next to the W, so it's closer to being solved. What do you need to do to solve for W? Yeah, how do you do that? Yeah, subtract the 2L to the other side will do? Yeah, let's do that. So 1,000, suppress the units, minus 2L is equal to W. What's the area of a rectangle? Length times width. Ah, but we already have a formula for what the width is. Let's try to use that. Let's plug this in there. Oh, good. Is that a quadratic function? And in order to take advantage of the vortex formula, which is on the previous page, but maybe I'll also put it on the board. I've only written down the x coordinate. So if we can get this thing into that form, we can read off the vortex. Is it easy to turn the thing that's written on the page into that form? Yeah, what is it? Yeah. Yeah, you distribute the L through. 1,000 L minus 2L squared. Maybe I'll even rewrite that in the other order. It doesn't matter what order you write these in. Is that enough information that it is now easy to write down the vortex? Yeah, so tell me, what is the x-coordinate of the vortex? So I guess this is answering the second of these questions. Well, the vortex formula says the vortex is at negative b over 2a, where a, b, and c are the coefficients. So, what's a? Negative 2. B is 1,000. All right, good. Everyone was just being very quiet. And I just wanted to make sure I wasn't just talking to an empty room full of people. So the vortex is at negative b over 2a. So negative b, you told me that was 1,000, over 2 times negative 2, and now you simplify. I think that's one you can probably do without busting out a calculator. Yeah. I think you lost a negative sign. Positive 250. Which is important, right? It would be very surprising for the ideal choice of the length of this rectangle to be negative. What that would tell us is that we're really just like the endpoint is going to be the right choice because we can't make a negative choice. Whenever you see something that's weird like that, you should take a quick sanity check because it's easy to lose a negative sign in this type of situation. Let's also recall the other part of the vortex formula, which is, again, not a part that you necessarily need to remember. If you want to see y equals negative 2l squared plus 1,000l, upward opening parabola or downward opening? Downward? Why downward? Because of that negative 2. Okay, so it's a downward opening parabola, so does the vortex maximize or minimize? Maximizes. The vortex maximizes. And since the y-coordinate is area, the vortex maximizes this parameter called area. So now I think we have enough to answer the whole question. Oh, that should be an L, not an X. L is the independent variable, not X. A length of L equal to 250, and let's put the units back, feet, and W equal to, well, I guess we need to figure out W, results in a maximum area of, and then I guess we should fill that in too. So we know that 250 feet will be the length that maximizes the area of this rectangle. Let's find the other parameters. So what's the width of this rectangle then? Or just the area? Just tell me one of those two things. Yeah. Width is 500. Why 500? Excellent. We have this formula that tells us the width. Cool. I think that's the easiest way to do it too. What's the maximum area? And I think that doing the actual arithmetic is the hard bit. How would you discover the maximum area? Sure. Yeah, great. We know the length and the width. Area is length times width. Here's one way. 250 times 500 square feet. And maybe you can figure out that that's like, I think 625,000? 125,000? Okay, yeah. I multiplied 25 by 25 accidentally. But I think that's the most informative answer we can give. So that's if you multiplied these two together. Could you also have just plugged L in here and gotten the same? So this is why I was saying I don't regard the y value of the vortex as being something that's a high priority to remember. If you know the input that gives you the maximum choice, just use that input and find the maximum choice. The y value of the vortex would be this number, 125,000. But I think finding that using b squared over 4a, c minus b squared over 4a would actually be the harder way to do it than just plugging in. So, in application, if you can use the vortex formula to figure out the x value, the input value of the vortex, then just plug in to find the output value of the vortex. That idea seems sensible? Groovy. So, the last one, I think I'm done talking for a little bit. Well, maybe I'll read the setup. So this problem was written shortly after the COVID semester when I started watching a person who rolls marbles down a hill as like a spectator sport. And records are tracked. The Marble League high jump world record at that point was held by a marble named Mandarin of the team O Rangers. If this marble leaves the ramp with an initial velocity of 285 centimeters per second, then, according to physics, that formula gives their height. When will Mandarin achieve their maximum height, and what is it? And as you get started, there's a subtle trick in like the 0th step. So start going through it. Walk with those around you. Absolutely any question is fair game. Yeah. Ooh, how many centimeters will we know? Oh. Yeah, centi is like Latin for 100. Yeah. Yeah, if this had been like using imperial units instead of metric, this would have been a wildly unfair question. If one were in inches and the other one in yards. I guess you can maybe remember that's 46. But. find how you make progress. So you can talk to each other. The room's very quiet right now, so. Some people coming down on single answers. Anyone want me to give some discussion right now? Okay, cool. If you're still walking and keep on plugging away, maybe the first a lot I'll give is, so what was the trick in this question before you could even get started? Yeah. Yeah, you need to deal with those units. You need to try to convert, I guess, everything to meters or everything to centimeters. Or you could do something like really wild, like convert everything to feet, but I think that would be silly. How many people converted everything to centimeters? How many people converted everything to meters? Cool. Maybe we'll pass through both. So if you converted everything to meters, then what is h of t? Well, I guess we already have this in meters, so let's leave that alone. I'm also going to put the t squared term out front just because this has the x squared term out front. I think it makes it easier to read the vortex formula. -5 t squared, and I'll suppress the units because everything's in meters now. Plus, what do you get when you convert this to meters? Yeah. Did you say 0.285? I think it's 2.85. You divide by 100. And at the end, we'll get a few possible answers. Maybe we'll do a few things to check. And what if you converted everything to centimeters? What did someone who converted to centimeters get? Well, I see 5 meters. How many centimeters is 5 meters? 500? Right, that's just what the centa in centimeters means. So this is 500 centimeters per square second. Oh, and I lost the negative. Plus 285 t. Groovy. And we want to optimize this. Well, we want to maximize. We want to know the time that produces the maximum height. So by thinking about the vortex formula, well, let's first decide if the vortex will maximize or minimize. Well, either one of those, if you were to plot that height function, would you see upward opening parabola or downward opening? Yeah. Downward. And that makes sense. Like the fall should go up and then come back in. So they'll have a maximum, and the vortex will maximize. So in each case, the vortex maximizes. Do we have everything written down that we need to find the vortex? Cool. So we have a vortex formula right there. In fact, how many people did find the time at which the vortex occurs? Cool. Well, let's do it then. Do I know what A is? What should I take for A? And if I'm doing, I guess this one was. -5 is an A. And what should I take for the B? 2.85. So the vortex maximizes, and the vortex is it's at a time value and not an x value because the independent variable is time right now. Negative B, 2.85 divided by 2 times -5. People feel good right now? How many people would want to use a calculator to compute that? Cool. I mean, that's fair. I think you can do it quicker without a calculator because what are you really dividing by? 10. And dividing by 10 just like moves the decimal place by 1. So it's not bad to use a calculator. So this is 0.285 seconds. Does that agree with anyone who did get a time at which the vortex occurs? Cool. Well, I asked you to tell me what time the vortex occurred earlier, and everyone was quiet, so that's why I'm doing it. Should we also do it for the one where we walked in centimeters instead? Is that worthwhile? Let's do it. Hopefully we get the same thing. Because when the vortex occurs, it doesn't depend on whether you think in terms of meters, centimeters, or miles. So let's just check that. The vortex is at t equals, let's see, it's -b over 2a. What should I take for b? 285 divided by 2 times this is the thing that's A. Is it also clear that that's just 0.285? Yeah, because you're dividing by this time 1,000, so you move the decimal place back. So it looks like the maximum height occurs not at time approximately, but at time at exactly 0.285 seconds. How could we figure out the maximum height now that we know when it occurs? Yeah, just say that with it.
Plug the t that you got into the equation.
Yeah, just take that t value, plug it into the original formula. Meters are centimeters false. Yeah, I'll tell you that. This is the same one. It seems to be on a really weird timing cycle when it does that. Meters? Centimeters? All right, I'll walk in centimeters. The formula in centimeters was this one. To find max height, plug in t equals 0.285. And again, we could do this by hand, but I think it's like just enough digits that I won't. So the maximum height occurs, so the max height in centimeters is -500 multiplied by 0.285 squared, because it's squared, plus 285 multiplied by 0.285. And again, that's something we could do by hand. In fact, I think there's some simplification you could do. You could factor out a 0.285 from everything. But instead, Well, I mean, you all have access to a calculator. Many of you have access to a calculator, so maybe there's not a whole lot of point in me doing it. What is that? 40.61 centimeters equals max height is wait, it was 41 point something, right? 40 point. Oh, you can't see what I'm writing. Jesus. Is that exact or approximate?
There's like a few other decimals, like 612 something. So like.
Okay. Yeah. Then I will leave this as a squiggly equal sign. All right. Groovy. That feel pretty good? Let's just answer one follow-up. The world record that preceded this high jump was a 48 centimeter record. This break it? Yeah. Cool. This idea of optimization, feel okay? So the game here is you have something that should be behaving quadratically. If you want to optimize and know like exact information, then try to turn this thing that should be behaving roughly quadratically, model it with a quadratic function. In the case that you have like some geometry to do, maybe you'll have some geometry to do, maybe you'll have like 2 parameters and you need to solve for one of them. Do that, write down a quadratic formula for the thing that you want to see, you want to maximize. And then just go through the motions. Does the vortex maximize or minimize? Then use the vortex formula to figure out the input that maximizes, and then just figure out all the other information. Feel okay? Nice. Maybe we'll do one last thing to double check. Suppose that I asked you to maximize this, but I gave you access to any electronic tool you wanted. What's something else you could have done to try to maximize? We could graph it, right? We know abstractly it should be an downward opening parabola, and we know that that's where the vortex should be. We can also pull up a graph, and we even, at this point, know what viewing window we should use, I think. So maybe I'll set the viewing window first. So the max height is 40-ish. So you'll set your viewing window in whatever calculator you are using. I like Desmos. There, that should be a viewing window that lets us see how high the vortex is. And the vortex occurs at 0.285 seconds, so let's go from 0 to 0.5 in the x direction. Reasonable enough? And this was using centimeters, so I better use the centimeters formula. Negative 500t squared. Oh, Desmos likes the independent variable to be x. Plus 285x. All right, and Desmos even does this handy thing where it tries to identify turning points. That agree with what we saw? Nice. I think the arithmetic went well. And even when you do everything by hand, especially if you have time to double check using a machine, do it. There's, a homework problem where you're going to do some optimization like this, and there's no reason to ever have a wrong answer at the end because you can check if your answer is right by doing stuff like this. Neato. Feel pretty good? So, with 10 minutes left on the clock, more than 10 minutes, 14 minutes, maybe I'll give 2 options. We could do one last example, or I could move on to thinking about inequalities. People want another optimization vortex formula example? All right, then let's do. So, I'm not going to run this as an exit quiz because the timing just isn't right to do that. So, the revenue, which the Once-Slow gains from sale of needs, which is of course a thing that everyone needs, is modeled by the following function. The revenue at price P is equal to negative 1/2 P squared plus 1900 P. And I have intentionally not included any units because the source material from which this idea is coming, no currency is specified. So, like something we can optimize? In fact, does this one look like an immediate application of Wojcik's formula? Yeah. So, answer the question. Let's see what you get. You to answer this particular question in the form of a complete sentence. If not in what you write, then at least like when you tell me what your answer is, tell me exactly what you think. Cool. If you're coming down on an answer, let me hear what you got. What'd you get? Yeah. Yeah, tell me that in a full sentence. Nice. How many people also plugged in that P into the formula for revenue? Cool. That's great. I mean, does the problem ask you to do that though? Yeah, so you could have saved yourself enough, but it doesn't want to also compute that. In fact, if someone asks you what price maximizes your revenue, it's probably a nice follow-up to tell them what the max revenue is. But in the context of like, I'll give exams and stuff, if you think at any point I'll ask you for the input that maximizes, and I'll give you the maximum output as one of the options on that multiple choice. I mean, I will. I'm telling you I will. So make sure to understand the problem carefully and answer exactly what's being asked, especially on multiple choice, because one of the things that gets tested for is can you read and understand exactly what the problem is asking. People feel good? Nice. So with 5 minutes, well, maybe I should ask this. Should I actually go through the problem, or did people feel good about it? Yeah, the actual arithmetic on this one I think was reasonably straightforward. At least finding P was, right? If you plug that in to find revenue, you probably needed a calculator. So let's close by, yeah, no sense in wasting 6 minutes. Let's start discussing the idea of inequality. And instead of starting with this setup, I think I want to jump right down here to this example. We'll do some setup to warm up next time. So, let's suppose someone asks you to solve x squared plus 4x minus 12 bigger than or equal to 0. Yeah, this is the one I want to solve. So, before we do any of this work, let's actually just look at a graph and see if we can eyeball it. So, let's just graph this. X squared minus 4x plus 4x minus 12. Let's go for a normal size viewing window. And let's just look at this graph and try to eyeball what x values result in this function being bigger than or equal to 0. These x values, is the function bigger than or equal to 0 for these x values? The function's like way up there. What about this x value? So it looks like there's a place where it changes. So by looking at a graph, we see a graph that looks something like that. From the graph, could we just eyeball where the places where it crosses the axis there? Yeah. Could we also find them doing like some amount of algebra? Yeah, we've got a quadratic formula that does that job. And I would like to know, where is this function bigger than or equal to 0? So it looks like all of these y values result, all of those x values result in y bigger than or equal to 0. So it looks like it goes all the way from negative infinity until, when does it stop being bigger than or equal to 0? Negative 6 is going to be an endpoint. Should it be included or excluded? Included. Why included? Yeah, because it's a bigger than or equal to. Plug in negative 6, you get y equals 0. But 0 is bigger than or equal to 0, so it should be included. Together with, when does it start being bigger than or equal to 0 again? Negative 2? Positive 2. Yeah. And then does it stay positive forever? Cool. So from a graph, you can just read off solutions to inequalities. That's not anything fancy. Let's think about whether or not we could do this without looking at a graph. Could we graph this just by hand? And let's not even think about the vortex formula. If you want to see that expression up there, it's going to be a parabola. Upward opening or downward? Upward. Could we also check for any x-intercepts using something we know? Yeah, I guess we could backdoor because we know we can because it's that integral value roots. But you can just find roots using the quadratic formula. Those roots will tell you these endpoints. Now you can look at a graph that you can draw by hand and figure out the solution without using a machine. So this is what we'll do an awful lot next time. We'll talk about solving quadratic inequalities, algorithmically, without the aid of a machine. Cool. So that's what we'll do next. I'm going to keep talking. You should be packing right now. I am done. I know I'm really bad at saying goodbye. I guess I'll be standing here while you pack up. If anyone has any questions they want to ask in a couple minutes before the next session. You too. Have a good day. See you.